Your Excellency, dear Mr. Hanko, thank you very much. It's a good morning, ladies and gentlemen. It's a pleasure and honor for me to be here with you today, in my home country actually, and contribute to a topic of utmost importance for the future of Europe. It's competitiveness in the area of research and innovation, which I guess we all agree largely determines the competitiveness of its economy, and this in turn is the basis for prosperity. I guess I should also, yes. The relevance of application-driven research in this context is self-evident. Less evident is the role of curiosity-driven basic research. My presentation is a plea for basic research, which is the only human activity that can lead to groundbreaking discoveries, to ones able to spawn disruptive technologies which can profoundly and positively impact our life and boost prosperity. I'll give you an example that addresses major challenges of our time. Some of the major challenges of humankind meets in the 21st century include stopping global warming and loss of biodiversity, maintaining prosperity in wealthy countries and perhaps even more importantly boosting it in developing ones, fighting thereby a two-class humankind which our planet accommodates today. Last but not least, protecting the health of all humans in the best possible way in high and low income countries likewise. I'll focus on this last challenge, which will also help tackle the previous ones. There is a pressing need, there is a really pressing need for improving the efficiency of protecting human health. Just as an example, every year 17 million people under the age of 70, science refers to this as premature deaths, of non-communicable diseases, die of non-communicable diseases such as cancer, diabetes, cardiovascular, and chronic respiratory diseases. 86% of them in low and middle income countries with a GDP per capita in the range of several $1,000s. As a result, newborns have a perspective for a healthy lifespan some 10 to 20 years shorter than their counterparts in developed countries. More than 3 billion people, almost half of the Earth's population, has to accept this gloomy prospect, and, understandably, more and more are reluctant to do so. We all know the consequences. It's not merely a moral duty to fight this two-class humankind. On the long run, it is a matter of survival of humankind on this planet. Highly developed economies fight the problem by spending enormous amounts for medical treatment in the lack of effective screening for early detection, and accept enormous economic losses due to the inefficiency of all those expensive treatments being applied far too late in most cases. In the European Union, these costs total to way more, actually really way more. I just wanted to share with you a round number. That's why I rounded down. It's way more than 1,000 billion euro year by year, per capita more than 2,500 euro per year. This makes it completely evident that such amounts are clearly unaffordable to low-income countries where the total GDP per capita is in this range. And people live, more than 3 billion people live in such countries. The only glimmer of hope for those more than 3 billion people is a cost-effective health screening that is able to catch the most prevalent killers in their early stage when treatment is much less expensive and has a much higher success rate. Such a transformation of healthcare from its current reactive mode to a future proactive, preventive mode of operation would not only benefit low-income countries, it would also save many lives in Europe and, in addition, enormous costs currently spent on inefficient treatments and incurred by losing the activity of valuable members of society. Hundreds of billions could be saved for better education, healthcare, and infrastructure to boost competitiveness and help maintain prosperity. Can basic research contribute? Yes, it can. I'll show you an example. The story I'm telling you started on the turn of the new millennium when our group at the Technical University of Vienna produced the first attosecond light pulses with which the fastest processes outside the atomic core, the motion of electrons, could be captured and reconstructed in slow motion replay, exemplified here by electron migration in organic molecules that make up our organism. This slow motion replay is performed with a time magnification of 10 to the 15, that is 1,000 trillion, equivalent in space to the magnifying power of the world's biggest space telescope. By the way, it's being also by a European organization, the European Organization for Astronomy in the South Hemisphere in Chile, plus the best electron microscope. Electronic motions are of utmost importance for our life, for our biological and modern life likewise, and probably that's why the Royal Swedish Academy found the ability to capture them worthy of the 2023 Nobel Prize in Physics, which, by the way, had been earned entirely on European soil. We have shown that the attosecond flashes tracking electronic motions are also enabling us to sample the oscillation of light waves, which occur on the same time scale as electronic motions. This ability, some 15 years later, opened the door to capturing what I would refer to as the heartbeats of molecules in human blood. And all of a sudden, somehow out of the blue, curiosity-driven basic research has spawned applied research of high societal relevance. Imagine we expose human blood plasma to an extremely brief infrared laser pulse, which brings the molecules in vibration. These vibrations are the heartbeats of molecules. Their frequencies are specific to the atomic composition and structure of the molecules. So basically, the signal that they make up, this one here in the frame, is a kind of a fingerprint-like information about these molecules. This signal comes in the form of an infrared light wave emitted behind the excitation. And whenever the molecular composition of the sample changes, this signal also changes. We have dubbed it, which basically contains all these heartbeats, as the infrared molecular fingerprint of the blood sample, simply because it comes in the form of an infrared wave. And this very infrared electric field molecular fingerprint can now be captured by highly sensitive attosecond metrology, which was developed for something completely different 20 years ago, right? So we could not possibly foresee that this thing, this ability, this new technical ability that has been spawned by basic research will be good for something that all of a sudden will offer the potential to open the door for something really important. This fingerprint signal is expected to change whenever emerging abnormalities change the sample's molecular composition, which we actually recently verified for several chronic conditions such as lung cancer. Why lung cancer in the first place? Well, more than 1 million people are being confronted with this devastating diagnosis, stage 4 lung cancer, where you have a prognosis for remaining lifetime of about 1 year, slightly more if you are lucky, and you respond to the therapies that are available. Capturing the disease at an early stage before metastases occur would greatly improve chances for long-term survival. Search for blood-based biomarkers enabling reliable early detection has remained unsuccessful so far, in spite of billions of dollars that have been spent on the development, discovery of just lung cancer biomarkers so far. Finding those individual marker molecules out of hundreds of thousands of different molecules human blood is composed of is like finding a needle in a haystack. Instead of searching for individual biomarkers, we propose to access the global molecular landscape and listen to the heartbeats of all these molecules that are there. And these heartbeats we excite by an infrared laser pulse. In collaboration with the Clinic of Pulmonology of the University of Munich, we collected samples over the years, of patients diagnosed with non-small cell lung cancer, the most common form of lung cancer, as well as samples from reference individuals, either healthy persons or patients with some other disease of the same organ. Out of the thousands of samples collected, we have selected 470 of lung cancer patients, samples of lung cancer patients, and the same number of samples of reference individuals free from cancer. We call them controls, with the two cohorts carefully matched regarding the distribution of the subject's age and other parameters like BMI. These are here the infrared electric field molecular fingerprints of all selected samples. Zooming in on a time interval, some 1,000 femtoseconds behind the excitation. The excitation you see on the left, it's actually just a trailing edge of the huge, strong excitation. And you see the ratio. The molecular signal is much weaker, but thanks to the sensitivity of attosecond technology, we can capture them. As you see, these very nice thin lines, which actually display the infrared fingerprints of the blood samples of cancer patients and healthy individuals. Cancer patients are the red lines, and healthy individuals are depicted by the blue lines. And you see that conspicuous differences between case and control fingerprint signals come to light at these later times after the excitation where molecular emission has taken command. These differences are caused by many, at present, not yet known molecules. But the beautiful thing is we don't even know these molecules. The main thing is that they cause these changes reproducibly and robustly whenever a tumor starts developing in your lung. And we can use these changes to distinguish the sample of a cancer patient from that of persons not carrying a malignant tumor in their body. Ideally, we shouldn't try this by human eye. Recognizing and differentiating patterns is one of the tasks that artificial intelligence excels at, vastly outperforming human intelligence in that respect. One can use a fraction of the case and controls molecular fingerprints to train artificial intelligence, briefly a lung cancer screening algorithm, and the remaining fingerprints are then used to test the trained algorithm. And here you see the classification efficiencies of the lung cancer screening algorithm trained and tested with infrared fingerprints. As you see, the classification efficiency is very moderate for stage 1, hardly reaching 60%, but gets close to 80% for stage 2, which is still early stage, and exceeds 80% for stage 3A, each of which are resectable, non-metastasized stages with good prognosis. These values are encouraging, but still offer quite some room for improvement. How to get better? More sharply defined reference fingerprints would allow the algorithm to more easily recognize aberrations caused by the disease. That's quite obvious, I guess. But how can we reduce the natural biological variability between persons used as controls, which manifests itself in this broad range of blue lines? It's not a sharp line, as you see. It's quite a range of different fingerprints for all the healthy individuals. Unfortunately, we can't reduce this between person variability. No way. We are all different to this extent. But we could replace the control fingerprints taken from other persons by a set of the same person's fingerprint collected before contracting the disease, provided that we collected them regularly in the framework of a screening program. We can simulate this reduced variability of control fingerprints, as you see on the left bottom diagram, shows the reduced variability of control fingerprints taken from one and the same person over time, and can use this and evaluate now just in computer simulation how our lung cancer classifier would perform in a setting where each cancer fingerprint would be referenced to a set of controls taken from the same person before contracting the disease. And here you see the result. Isn't it incredible? Isn't it incredible? Dramatically improved classification efficiency of early stage lung cancer, stage 1, more than 90%. To the best of our knowledge, completely unprecedented values for early stage lung cancer, in spite of the billion scale research for individual molecular biomarkers. Meanwhile, infrared fingerprinting has proven its capacity to detect quite a few other conditions, altogether 8 different types of cancer. That's the number we have looked at so far. All types of cancer that we have looked so far basically, obviously, leaves their signature in the infrared fingerprint of blood samples, and several other major non-communicable diseases, such as highly prevalent cardiovascular, metabolic, and respiratory disorders. These classification efficiencies have been obtained, once again, with reference fingerprints collected from other persons. Based on our proof of principle lung cancer study, we may be able to capture all these conditions in their early stage of development if the references are collected previously from the same person. This is only possible if they are donating blood regularly whilst being healthy. This prompted us to establish the Center for Molecular Fingerprinting in Budapest several years ago, and roll out a large-scale nationwide longitudinal study, the Health for Hungary program, back in 2021 for following up 15,000 individuals across the whole country. They have been donating blood samples, several ones during the first year of participation, for allowing us to determine their personalized baselines, and 1 sample per year afterwards to monitor their health trajectories. The preliminary analysis of infrared fingerprints, here shown in a spectral domain, of the first 4 blood donations of more than 2,000 study participants, corroborates the hypothesis that the variation of the fingerprint of any person over time, this is the violet curve, any person over time is substantially smaller than the differences between healthy individuals, shown by the red curve. As we have seen before, using these individualized references is the key to early detection of severe chronic conditions leading to 17 million premature deaths every year. In our study, initially, none of the participants is diagnosed with any of the 4 major categories of non-communicable diseases displayed here. During the 10-year study period, however, we expect more than 1,500 cardiovascular events, more than 800 participants diagnosed with diabetes, more than 500 with COPD, and more than 160 with lung cancer. Their blood samples taken at the time of the diagnosis and before will be invaluable for testing and validating the capacity of infrared molecular fingerprinting and possibly other liquid biopsy approaches to answer the overriding question: what is the most economically viable set of health data that enables comprehensive and reliable monitoring of human health? Which directly leads us to the question whether molecular fingerprinting and/or profiling of human blood can provide sufficient information for health screening. Our quest for the answer is driven by a vision which was beautifully formulated by our research director, Michael Žigman, from Slovenia, by the way. Imagine a tool that could catch issues before they become significant problems, like a sensitive radar, but one that is affordable to everyone, very important, that is affordable to everyone, not only in wealthy countries where we have the luck to live, not only there, but everywhere on this planet, and is fast and easy to use, to detect irregularities well before individuals get symptoms or would even think about seeing a doctor, to nip potential health hiccups in the bud, promising help to keep us on the road of well-being. More than 100 researchers from a dozen of countries of the European Union, from several ones from Asia and North America, teamed up to pursue this vision, based here in Budapest and in Garching, near Munich. So far, 3 institutions: the Ludwig Maximilian University of Munich, the Max Planck Institute of Quantum Optics, also in Munich, and the Center for Molecular Fingerprinting based in Budapest joined forces to pursue the grand goal of establishing a new cost-effective screening platform for the 4 major non-communicable diseases killing some 75% of the population of our planet, including 17 million premature deaths every year. But given the importance of the grand goals pursued here, it is more than likely that this bilateral German-Hungarian project soon becomes multilateral. We are in discussion with His Excellency Minister Polasek from Austria, who was supposed to be here today, but unfortunately couldn't come due to the events from the last few days. And his ministry in Vienna is about to actually discuss with us how Austrian research institutions could also join in. Also, Wrocław University from Poland is about to come aboard, but this was temporarily halted by the European Commission's decision from December 15, 2022, to exclude several Hungarian universities from the European funding programs, preventing, unfortunately, a Munich-Budapest-Wrocław consortium from applying jointly for an ERC starting grant, as well as, unfortunately, preventing several other interested ERC grant holders to join this endeavor. Before others join us to invent the future, in this particular case, the future of healthcare, the research that seamlessly turned from curiosity-driven basic research to mission-driven applied research is being implemented in Munich and Budapest, and I would like to invite you to a virtual tour through our fingerprinting laboratories, if I'm allowed, just a couple of minutes.
Of course.
I think you will enjoy this. A virtual tour through our fingerprinting laboratories operated on the research campus in Garching at Munich. It's just in the north of Munich, halfway between the airport of Munich and downtown Munich. Here you see where the thousands of invaluable plasma samples are stored and prepared for fingerprinting measurements, which is happening in this laboratory. With the next generation instrumentation, the Infraslampler 3.0 class being developed in a clean room next door. While the blood samples, along with accompanying clinical data, are being collected from 15,000 individuals, the Center for Molecular Fingerprinting is planning and building its new home on the central campus of Budapest, a few hundred meters away from here. The CMF building will include a state-of-the-art cryogenic biorepository, one of the most modern in the world, for handling and storing the 200,000 blood plasma samples to be collected in the H4H study, along with a database of comprehensive health data of the study participants. Furthermore, state-of-the-art fingerprinting and profiling technologies for comprehensive molecular characterization of human blood will be accommodated, yielding an infrastructure and clinical sample collection that are second to none in the world. if you agree that the grand goals pursued here are important for Europe and the rest of the world, you will also agree that it is in the interest of Europe to encourage its best scientists and research institutions to help this endeavor succeed. To the benefit of the next generation of all Europeans and to the benefit of the world. Thank you very much.